Hello and welcome to a short video on a topic that goes by various names. You may see it called local linear approximation, you may see it called tangent line approximation, you may see it called exploitation of local linearity. It all means the same thing, and it's all pretty easy to unpack if you have some background in differentiation and finding the equations of tangent lines. We're going to begin by assuming that we have some compelling reason for wanting to know the square root of 14 to reasonable precision. Unfortunately, we haven't had the foresight to have our calculators with us. Slide rule's in the shop, so we have to fall back on our wits and our pencils as a way of trying to get a pretty decent approximation. We're interested in the square root of 14, so we would like to know the answer to the question, if I plug a 14 in to the square root function, what do I get out? And certainly it looks as though we're going to get out something not very much less than 4, but can we do better than that? And the answer is yes. And here's the thing that we're going to exploit. And you may recall having encountered this when you first started talking about differentiation. If I zoom in on the graph of a differentiable function at a location where it's differentiable, what I see is that it looks more and more and more like a line the closer in I go. And the line that it looks more and more like is the tangent line. So the thing that we're going to try to do is to find the equation of the tangent to the square root function at some reasonable location in the neighborhood of x equals 14, use it to get an estimate, and then kind of take a look at what the quality of that estimate might be and when we might be able to use this and when it might be a little more challenging. So we have this notion that we can approximate the graph of the square root with a tangent line. And we need to be interested, of course, in what the point of tangency is going to be. And I'm going to suggest that we use x equals 16. We want to satisfy two requirements, both as well as we possibly can. The first of which is that the value be easy to work with, because the whole point of this is that we don't have mechanical aids to help us do the arithmetic. And the square root of 16 certainly is an easy number to calculate. The second requirement is that the point of tangency be reasonably close to the value that we're interested in, and that was x equals 14. So let's go ahead and get the equation of the tangent to the square root function at x equals 16. F prime, of course, is 1 over 2 root x, and f prime of 16 is 1 over 2 times the square root of 16, which is 1 over 2 times 4, which is 1/8. The y-coordinate of the point of tangency, which just for the record is f of 16, is 4. And so the equation of the tangent line is y minus 4 equals 1/8 times x minus 16. And if we slightly rewrite that, it is y equals 4 plus 1/8 quantity x minus 16. This should be a very familiar exercise for those of you who are watching this video. And so now we ask ourselves, well, what happens if I plug a 14 in there? So I'll say y of 14 is 4 plus 1/8 times 14 minus 16. It's -2 divided by 8 is -1/4. So I have 4 minus 1/4, which is 3 3/4, or 3.75. So 3.75 is the local linear approximation of the square root of 14. It's the value that we arrived at by using a tangent to the square root at a value near 14. So let's go back and see how that looks on Desmos. So here again is the graph of the square root function, and I am going to add to my graph the tangent to the square root function at x equals 16. And as you can see, there's quite good agreement, at least visually, for a while here, maybe from the mid-teens up toward 20. And in fact, if I slide around and if I turn on some labels, maybe even give some coordinates, you can get a sense for how this looks when we're right at x equals 16 or very close. Of course, we have a perfect fit at x equals 16. We have a very good agreement for values, depending on what you mean by good, somewhere in this neighborhood. So we had plugged in 14. Re-enter this here. So we had plugged in 14, and we got, as you'll recall, 3.75. The actual value calculated by Desmos is 3.742. So it's a pretty good approximation. But of course, it's important, if your approximation is going to be a good one, that you are reasonably close to the point of tangency. And reasonably close sort of depends, right? And it has to do basically with how hard the curve is bending. If the curve is relatively flat, if it's not particularly convex or concave, if you're familiar with those terms, the tangent line is going to give pretty good agreement for a while. The more strongly the curve is bending, and the farther you are from the point of tangency, the more trouble you're going to end up having. So that's all you really need to know. If you need to make an approximation of this kind for reasons of practicality or because somebody who wrote a test is asking it of you, you just find the equation of the tangent line at a point that is reasonably close to your value of interest, but convenient to calculate. Get that equation, plug in your value, that's your approximation. For the record, there are formulas, and we should talk about how that looks. You almost don't need to know them in order to use this process successfully, but just for the record, the tangent to the graph of f at some value of x equals x naught, I'll write it down, tangent to the graph of some function f at x equals x naught. What's that going to be? Well, the slope of that tangent line is going to be f prime of x naught. And the point of tangency is going to be x naught f of x naught. So there's the equation of the tangent line in sort of formal notation. If I move over the f of x naught so it's solved for y, you see it in a form where it's often encountered. Now this is along the tangent line itself. This is the equation of the tangent line. Close to, whatever that means in a given context, close to the point of tangency, values of the function are approximately equal to this. And so this is a thing you'll fairly frequently see. Sometimes this equation is rendered a little more compactly as something like delta y equals f prime of x naught times delta x, the idea being that there's some increment in the x that corresponds to some sort of increment in the y. But at the end of the day, you don't really need to know these formulas, although they shouldn't be that hard to get your head around. You just need to fall back on the very basics from when you were first learning sort of the point of differentiating. So that is local linear approximation. I hope that it has been helpful. Happy mathing.